Okay, good morning. Really happy to see everybody here. Very excited. I'm excited. I hope you're excited. First day of reInvent. I can't believe everyone's here. This is fantastic. You all look so fresh-faced, right? It's not like it's Friday and everybody's tired, wanting to go home. Welcome to our session, Ground Station Digitalization with SDRs in the Cloud. My name's Alistair McLean. And this is my friend and colleague, Ajit Rajdev Singh.
Hi, everyone. I'm Ajit Rajdev Singh. I'm a principal solutions architect. I'm based out of Luxembourg in Europe.
And I'm based out of New York. So today, here's the agenda. We're going to go through a number of topics. First of all, we're going to sort of level set and think about what is an SDR, what is a software-defined radio. We're going to go through some Amazon EC2 accelerated compute capabilities, okay? We are going to then talk about a couple of use cases with satellite communications versus sort of Earth observation use cases and how the SDRs can be used differently in those use cases. And then Ajit's going to take us on a deep dive into FPGA programming. This is a 300-level session, okay? So we are going to go fairly deep. We're going to then talk about the EC2 F1 development workflow and how that is coordinated and how that works. We're then going to talk about how to get really high-performance network access down to the FPGA with the Data Plane Development Kit, or DPDK. Then we've got a demo video that has a packet generation demo that we can show you how to do that. Then we'll summarize. And what's really cool is after this talk at 12 o'clock in the peer talk room, we will be there for one-on-one chats if you want to come and talk one-on-one, ask us questions. We're very happy to do that. So on with the show. So what is an SDR? Well, it's a software-defined radio. It's a radio communication system, okay? And what we see is components traditionally have been hardware-based, okay? On the ground, next to antennas, racking and stacking, analog hardware, digitizing feeds from satellites. But what's happening and what we see across the industry now, and I think the term software is eating the world applies here, it's also eating space, is this move to digitalization, this move to virtualizing parts of the hardware processing stack. And really it's this move from sort of hardware defined radios, or hardware radios as we call them, into this software defined land for the components that make sense, okay? You can't fight physics. There are some components that live very nicely right next to your antenna that require very low latency, that require certain aspects of physics to operate. But we are seeing customers now running quite a lot of the stack in AWS, modems included. And we'll talk a little bit about why that is. We're beginning to see this happen on both virtualized hardware and edge devices as well. So if you have an edge device with the capabilities that we're talking about here, a lot of that now is moving into these edge devices. And also if you have a high bandwidth network link, it's also happening in the cloud. So really this is it's a very rapidly evolving space, okay? Lots and lots of customers are looking at doing this, some are doing it already. You can buy SDRs, for example, in the AWS marketplace today, right, and run them. And really, the hardware advances that we have now and the access to compute in the cloud, elastic compute in the cloud, that has this level of performance, really kind of starts to render practical, lots of processes that were once, only sort of theoretically possible. Now you can do things like demodulation of DigIF feeds at very high rates of bandwidth using these systems and then switch them off when you no longer want to pay for them, right? So this turns the business case from sort of a traditional you have boxes, you buy boxes, and those boxes last a certain number of years, to, hey, look, we've got a new FPGA, or we've got a new GPU that's out. Let's use that capability for our modems. Let's change the way that it's processed. In order for this to happen, we require hardware acceleration, okay? And by hardware acceleration, the reason that we need it is these digital signal processing, DSP algorithms, are embarrassingly parallel, okay? So you need something that can take advantage of that. And you can use specialized hardware, so I'm talking about vectorized instructions, such as AVX512. You can use GPUs, and you can use FPGAs in order to give you that acceleration that you require for that parallel method of working, okay? Being able to process lots of data at once at very high rates of bandwidth. EC2 accelerated computing instances use hardware accelerators or coprocessors to perform some functions such as floating point math, graphics processing, matrix calculations, that kinds of thing. And it's more efficient than running software on more generic compute, okay, by not leveraging specialized functions, for example. Once you can leverage the specialized functions of the hardware, whether it's the chipsets, whether it's the instruction sets, whether it's a combination of all of them, you can gain a lot more efficiency for your sort of per node processing power, if you like. They offer more parallelism. They offer higher throughput, okay? And we have various types of accelerated compute. We have a very broad portfolio of accelerator choices here at AWS, whether that's our instances with AVX512 that I've talked about, GPUs, FPGAs, or custom ASIC-based instances like Inferentia and Trainium that we build ourselves and we use for machine learning use cases. So this really is the kind of the slide here. It's a bit of an eye chart. I'm not going to go through every single instance type because I think I'd bore you all to sleep on this Monday morning. However, the takeaway here is that we have partners and we have a very large portfolio, very broad range of different types of accelerated hardware. It's not just all x86 or ARM. It's very much, it's x86 and a GPU, or it's ARM and a GPU, or it's x86 and an FPGA. There's lots and lots of capabilities that customers today that I speak to on a daily basis take advantage of. And that led us to build this talk. And because a lot of customers were asking, well, how does this fit into the satellite industry? And how can I actually leverage some of this power in my use cases that I have? So we built this talk primarily to answer that question. And there will be time for some Q&A, but really the best Q&A is probably going to be done in the peer talk session afterwards if you want to really get into this stuff. We live and breathe this stuff, by the way. So we're very, very pleased to talk about it at all times. So why FPGAs specifically? Right? Let's focus on those for a little second. Really what we're trying to model here is digital signal processing, okay? So if you imagine a very, very simplified view in this 3-block diagram, okay? You have this analog signal that will come off a satellite. You have this analog to digital converter. That's, some kind of process. And then you have the digital signal processing. And this really is, and by the way, this is bidirectional because we have customers that initiate in the cloud and send out as well. That's perfectly possible. And then what you can do really is do this loop for business, to get business value. Really what you're trying to do is convert this analog signal coming off of the satellite into SAR images or Earth observation pictures or a satellite feed or, vessel information. That's really what we're trying to do here. We're trying to accelerate the time to value. We're trying to accelerate business value by leveraging this accelerated compute. Now, as I mentioned before, this process requires very many processes to be performed in parallel, which is why FPGAs are perfect for this, because they are integrated circuits that can be programmed in the field. That's kind of the whole point. They are adaptable. You can put new images on them, you can give them new capabilities, and those new capabilities and images then run at the speed of the cards. They're very suited for parallel algorithms because of the way in which the architectures are run. It does obviously require you to be able to program to that model. And they also have very high bandwidth memory. Okay, so you want to be able to take lots of chunks of data into a big vector, process them all together, spit them out at the end, make pictures, dump them into S3, and then give them to your customers. Right? It's really what we want to do here. But we need gigabits of networking. We need gigabytes of memory transfer. We need really high speeds and feeds here. EC2 F1 instances today have around 6,800 DSP engines within each instance type. We'll talk a lot more about that in Ajit's part of the talk and how to leverage really the best way to leverage high bandwidth networking as well. Okay, so let's talk about use cases for satellite modems, and I've chosen two here, pretty straightforward. We want to look at SATCOM, satellite communications, versus Earth observation. That's how I'm choosing to sort of split them out, and I'll talk about why that is. In SATCOM, we look at typically always-on connectivity, okay? So you're gonna have your modem constantly running, you'll have a feed, okay? So this is typically used for broadcasting a sporting event, all right? The Formula One was here last week, for example. You can go from your camera into your receiver truck or your transmission truck, send it up to a satellite, and that satellite will then send down information to waiting receivers on the ground. These are geostationary, which means that they hover above one point in the Earth constantly, and they have many thousands of beams. And some of the latest ones that go out, many thousands of beams can be trained on various targets. And my colleague Alan Campbell wrote a great blog piece about predicting spot beam placement using machine learning. So it's really meant for relay. And it's high throughput, fixed in space, as I said, usually in equatorial. And they serve multiple customers with multiple beams. Now, you have to think about how you would then transform and use that in the cloud. If you were running a SATCOM modem in the cloud, for example, and you can, and people do, you would need to take advantage of the cost of running that. So we have various means of bringing that cost down to make that more economic, to be able to run that with whatever hardware that you want to use. Let's contrast that to Earth observation. So now what we've done is drop much closer to the Earth. These satellites are now in constant motion around the Earth. And they may be 1, 2, there may be 1,000, several thousand. This is in low Earth orbit now, or LEO. Now, typically the contact duration for contacting a LEO satellite is intermittent, anywhere between sort of 8 to 15 minutes at a time, depending on what you're doing, depending on where you're placed. So you have to then think, okay, well, I'm only receiving or sending data at certain times, but I'm paying for my traditional modem all the time. Wouldn't it be cool if I could match my modem usage to my actual data transfer? And with AWS, you absolutely can do that, and we have customers doing this today. We talked about how it's in low Earth orbit, and the latency is very much lower compared to a geostationary satellite. So geostationary maybe up 750 milliseconds round trip time. With LEOs, you're looking at around 50 milliseconds. Okay, and there is also medium Earth orbit, which is around about 150 to 200 round trip time milliseconds. So you can sort of see the various use cases. That's why you can use, and companies such as Kuiper, Starlink, OneWeb are doing this today. You can do things like real-time video over them, for example, and it's an amazing bit of technology. when you have large constellations of these, like other customers do, then you can start to have global coverage as well. So the satellites move in a very defined, well-defined ground track during their orbit, and it makes it easy to predict, or easy-ish, to predict where they're going to be and when that contact's going to be available next. And you schedule these contacts at multiple ground sites. So what you would want to do then, using the cloud, is to be able to send that, digital IF, if you like, intermediate frequency, back to the cloud to do the demod decode in the cloud during a contact window, and then shut everything down, right? Then you can match your data transfer by cost, and it becomes more of a, if you want to scale, it's now sort of more of a financial decision rather than an engineering decision, right? You can just spin up more if you need more. You can spin down if you need less. This is the benefit of the cloud all over again, okay? This is just applied to the SATCOM industry now. So that's my portion of the talk done. I think you've got a good feeling of what we're going to be using and why, and the various use cases that we have, and how business value is generated from each different type of use case. Ajit's now going to run us through how the F1 instances actually work and how you can program to them. And we're going to go through the demo and sort of work up with the summary. So Ajit, please take it away.
Perfect. Thank you very much, Al, and for describing the various use cases for satellite or software-defined radios and for SATCOMs and Earth observation. In this part of the session, I'm going to talk to you about the world of FPGAs as it is in AWS and the F1 instances specifically, right? So a quick refresher, what is an FPGA? FPGA, or Field Programmable Gate Arrays, as they stand for, are a matrix of semiconductors that are essentially connected, or there are configurable logic blocks. They are connected with programmable interconnects. So essentially think about your AND gates, your NAND gates, XOR gates, a bit more complex logic functions, connected in a way that you can actually change the configuration and build very complex logic around it, right? So these are your hardware Lego blocks that you can use after the board is manufactured and program it to your application logic. And this ability of FPGAs to be programmed after they are manufactured makes them extremely efficient, right? So you can connect or build the hardware in a way that it is purpose-built for your workload. And this efficiency is highly needed in satellite communication workloads, right? As Al mentioned, you need high amounts of parallelism. You need to be able to do different things in different blocks. And this ability to program it allows you to kind of really build it in a very efficient manner for your workload. So now that we have established that FPGAs are being looked at customers and customers are looking to build their software-defined radios with for both SATCOM and Earth observation with FPGA. So what really is the blocker for them to adopt FPGA? So let's take a look at the challenges. The primary challenge for customers to start building with FPGA is the initial cost of development. And this cost involves purchasing of the FPGA hardware, which can vary depending upon what manufacturer you choose, what capacity you want, what performance you want from the FPGA, and so on. Similarly, like customers are always thinking about, okay, how much should I invest in what kind of FPGA? What should be the cost of my initial board? And like they try to balance it with the long-term cost saving. Like, will I get a return on this investment, right? So most of the customers end up spending a lot of time doing this balancing act, and they lose the ability to experiment. They lose the agility to go to market faster. So that is the very first challenge. The second challenge is setting up of the FPGA dev and test environments. FPGA development is more hardware oriented, so it has a specific set of requirements as compared to a typical software development environment, right? The FPGA development tools environments are typically provided by the vendor of the FPGA, and they need to be configured and set up properly so you get the best out of and the most out of your FPGA environments. And finally, getting all of the, so you have the hardware environment, you need to be able to you need to be able to simulate it. You need to have hardware simulations inside your FPGA, and setting up of all the simulation environment and setting up of the stimulus is a complex job. And when you have set up all of this, you need to be able to have a harmony between your development and the test environment. So there is this challenge with setting up of the development and test environments. And finally, once you have built your product based on FPGA, you need to be able to support it in production environments. So the third challenge is deployment of your products, maintenance and operation, ongoing operation of your FPGA based products. These products, I mean, it's not just a software where you just deploy to a cloud instance or a container instance and it's up and running. When you want to have your SDRs or when you want to have your modems built on FPGAs, you need to be able to, you start thinking about what is going to be the rack module where I will put my modem, what is going to be my deployment function, like how will I deploy software updates to that rack and that hardware installation. How will I do ongoing support? If there is a reprogramming needed for doing that, how will I go about reprogramming my FPGA boards? So these are the challenges why customers are looking at cloud to build their FPGA-based modems, right? And now I want to go into the AWS EC2 F1 instances, which provide FPGA capabilities that customers can leverage to build their software-defined radios in cloud. So in a brief overview, you can see the FPGA or F1 instances are powered by Xilinx VU9P FPGAs. Each instance can be from one FPGA board all the way up to 8 FPGA boards, depending upon the instance size you choose, right? And each FPGA board comes with a 64 gigabit DDR4 memory with error correcting channel for high data reliability. Similarly, the FPGA boards are connected to the host system using a Generation 3 PCIe bus for high data throughput. And each FPGA board has 2.5 million logic cells, and as Al mentioned, they come with 6,800 DSP or digital signal processing engines. And this is characteristic of each board, right? And if you can have like 8 boards in your into your instance, you can essentially multiply this by 8 times. And the table below shows you the spectrum of the instances. So we have on the lowest spectrum the F1 2X large, which has one or a single FPGA board and supports a networking bandwidth of up to 10 Gbps. While we have the F1 16X large on the most widest or the largest of the instances, which has 8 FPGA boards and can support networking bandwidth of 25 Gbps. So now that we have seen the capabilities of EC2 F1 instances, let's dive into the architecture of how these instances are actually built, and like we understand that to be able to build our products on it. So this is a block diagram of the EC2 F1 instance, and I will mostly focus on the FPGA. So these 2 blocks represent the FPGA boards, the FPGA board. And you can see that at a high level, the FPGA board is divided into 2 blocks. The first block is the FPGA shell, and the second block is the custom logic. The FPGA shell is the AWS managed, it actually implements the AWS platform logic to manage your FPGA instances or FPGA boards. While the custom logic block is the one where FPGA developers build their custom logic and load it into the board. The FPGA shell itself is divided into 2 physical functions. The application physical function, as indicated by AppPF, and that physical function is used to access the custom logic of that is running in your custom logic block. While the management physical function is used for managing your FPGAs, DMA, PCIe, interrupts, and so on. So that is purely used by the FPGA shell block. Essentially the FPGA shell itself consists of multiple base address registers, and these base address registers are mapped to the memory input-output of the host instance. So you can manage the base address registers and how they are accessing and how they are connecting to your application custom logic using the base registers which are mapped onto your host itself. The network access, as you can see, is also connected through PCIe buses, and the network access is provided using your normal VPC constructs like elastic network interface or the enhanced network adapter. So both the FPGA board and the network adapters are connected to the host system using PCIe buses. So now that we have seen the architecture and how the various interconnections work and how they are connected inside the host, let us take a look at the development environment and the development life cycle of a product that you want to build with AWS F1 instances. So this slide indicates the entire life cycle where you start with the Amazon machine image. We provide a F1 specific image or FPGA development and Amazon machine image. This image comes pre-built with your FPGA development environments, which can be either hardware development environment like your Vivado, or a software development environment like SDAxle or Vitis, right? You can use this machine image and the development environment to build your logic, custom logic, and then compile that custom logic into something called as the Amazon FPGA image, or a short form is AFI. Once you have built this AFI in the host system, you can load that AFI onto your FPGA board, and you can choose which FPGA board you want to load. Like if you're running it on a 2x large instance, you have a single FPGA slot. But if you're running it on a 16x large, you have 8 FPGA boards. So you can choose what AFI you want to load onto what F1 on what FPGA board. A really cool part about this development cycle is that these two pieces, the Amazon machine image, the development environment, and loading of AFI are completely disconnected in a way that you can essentially build a development environment on any general purpose and compute instance, a cheaper instance, which actually can lower your cost of development. You can use the development environment, the hardware development or the software development environment. You can use the simulation engines that come pre-built inside the AMI on these instances, build your AFI, and then store that AFI into an S3 bucket, say for example, and then download that and load that onto an F1 instance that is either running in your test environment or production environment. So this decoupling allows you to lower the cost of your development environments as well, and really kind of tailor what kind of development ecosystem you want for your sandbox environments. So some details on the AWS FPGA Developer AMI. The FPGA Developer AMI is something that you can subscribe from the marketplace free of charge, and it, as I mentioned, it comes pre-built with things like Xilinx Vivado for hardware development environments, as well as virtual JTAG for interactive debugging. And you also have software development environments, as I mentioned, like Vitis and SDAxle. So bringing it all together, and this slide really captures the decoupling that I mentioned, right? So you actually can have a C5 or M5 based development environment. You can load the FPGA Developer AMI onto it and use either a hardware development environment or software development environment to build your custom logic. Once you have built that custom logic, you compile that into an Amazon FPGA image or AFI with a single line command that you can see in the screenshot. And that AFI, you can either put it into an S3 bucket for later use for deploying somewhere else. You can directly send it to an F1 instance that you want to load that image onto, which can be either directly in your production environment or in your dev environment. Or as Al mentioned earlier, you have the option to sell or provide this AFI to your end customers as your own product through AWS Marketplace. So you can even list that product on AWS Marketplace, and your customers can subscribe to it and download it in their own environment. So now that we have looked at the development environment, how the development works, I want to explain the network access to the FPGA boards, because it's not typical where you have your hardware and you have an RJ45 cable plugged directly into your FPGA board. We are running an EC2 instance, and this thing we saw is the host is connected to the FPGA board and the network access provided through VPC construct. So I want to dive into how the network access to the FPGA board will work in the EC2 environment, and specifically with DPDK. So let us go into the details of why we recommend using Decoupling development kit to build your network access inside from your external world to your FPGA boards. So what are the advantages of using Decoupling development kit, or DPDK for short? Firstly, you get cloud native network security. So you are already familiar with the security constructs for network interface in AWS EC2 instance, right? You know how to create security groups, you know how to manage them. Maybe you also have a security hub where security manager from where you are managing your security groups centrally. You would want to use the same kind of constructs and have a uniform security policy to be able to manage access to your FPGA boards as well, right? And using DPDK-based environments and existing VPC networking constructs, you're able to do that. Continuing to that benefit, you can apply the same network policies that you have. Say, for example, you are using a transit gateway, and you are using transit gateway routing tables to manage access to your instances. You can extend the same concept to make sure that you are using the network policies of your transit gateway to also manage the network access to your FPGA boards. And finally, Decoupling development kit applications are not residing in the kernel space. They actually sit in the user space, and they use this capability of poll mode method, where essentially you are not relying on kernel interrupts. The Decoupling or DPDK application continuously polls your network interfaces, and it really allows you to get to a very high network throughput. And the ability of running an application, network application in user space, provides you the ability to kind of build a very advanced and sophisticated network capability, right? In kernel space, you are limited, but in a user space, you really have the ability to build a sophisticated application. And DPDK applications really allow you to do that. They provide you with very advanced packet processing capabilities. And I have a demonstration to show you this eventually, and we will see what I mean by this. So let us take a look at a flow of network or a packet as it goes through the F1 instance and through the DPDK application, right? So in this diagram, you can see three major blocks, or firstly two major blocks. This big block is the is the EC2 instance, and the block here is the FPGA board, right? And the instance itself is further divided into two blocks. The first block is the user space, and the second block is the kernel space. So you can see in the kernel space, you have networking stack, you have the ENI adapters, you have the ENA adapters, and you have the PCIe generic standard, right? And then in the user space, you have the DPDK application and the DPDK environment, and you have the PMD drivers for various components. So there is DPDK support for enhanced network adapters as well. So you can see the DPDK ENA PMD driver, and then there are other drivers that allow you to build these sophisticated or advanced integrations. And on the FPGA board side, you have two further blocks. One is the shell, which is the AWS managed part, And the custom logic part that you can see 2 blocks in it. These 2 blocks are the ones that provide network connectivity into your FPGA instance. This block is called the streaming data engine. And they actually attach to your PCIe channels to be able to get network traffic directly from your enhanced network adapters through the PCIe bus and then into the shell using the SD instance. So you can see a packet as it enters the enhanced network adapter receive queue. It goes directly into the DPDK application. It completely bypasses the kernel stack. The DPDK application can be then processed or can be configured to have some advanced processing on it, and it sends it down through a software patch panel driver. This software patch panel essentially patches your enhanced network adapter with the SDE block that we are running in the FPGA, and then sends it directly into your custom logic environment.
So just to sort of put a point here, I mean, I really like this model because imagine you have packets coming off of your antenna, you push them into AWS, they may not be sort of data packets, if you like. You may have telemetry from the antenna, you might have metrics to do with power or anything like that. Using this pattern, you could take those metrics, those non-sort of customer-facing packets, send them to some kind of analytical capability, hosted in AWS as well, and then just send on the data packets down to the card. So you kind of reduce some of the bandwidth on the card, but you also enable sort of full telemetry and access everything that comes out of your digitizers or whatever it is that you're sending in. So just think of this as a packet flow, and there's a lot of different capabilities that you can do here in terms of analytics.
Absolutely, Al. So as I mentioned, the DPDK application can be really advanced, and you can really punt a packet either to your FPGA board or into your Grafana or Prometheus stack. If it's just a monitoring or a logging packet, you don't need to send it out down to your FPGA boards, right? So you can really build these complex processing rules inside of your application. And on the way back, so the packet generated from your custom logic goes first through the SDE transmit queue, goes into your DPDK application, gets processed there, and then the DPDK application patches it to your transmit queue inside the enhanced network adapter. So inside an FPGA instance, the DPDK application, as you can see, typically consists of 2 functions, right? One is the DPDK application that is running in your user space, and the other is the SDE block along with your custom logic application. But the networking stack itself are 2 components. One is the DPDK application running in the EC2 instance or the host instance, and the other one is this SDE block which is running on your FPGA board. So I want to bring all of this together with a demonstration. And the demonstration is to show you what kind of packet throughput we can get with FPGA instances, right? So for the demonstration itself, I have a very simple setup. So you can see in this, I'm hosting in EU. I have my environment hosted in EU West 1, which is the Ireland region. I created a public subnet to make sure I can access into my instances with SSH inside a VPC. And there are essentially 2 instances that I created for the demonstration. One is the F1 2x large instance, the smallest instance, which has the virtual Ethernet application. And it has an additional interface which will be used for the DPDK piece. The second instance is an M5 8x large instance. It hosts the DPDK sample packet generator application, and it also has an additional Ethernet interface which we will use dedicatedly for the DPDK piece, the DPDK application, right? As I mentioned, when you actually have DPDK application, you are moving away from kernel space. You attach this interface into the DPDK environment, and we will see that in the next slide. So now we are inside the virtual Ethernet application instance, which is the F1 2x large. Let's take a look at the interface config on this. And as I mentioned, there are 2 interfaces. ETH0 is for SSH, and Ethernet 1 is the one we will use for our application, for our DPDK application. So let us check the software patch panel status of the DPDK application. And you can see both the interfaces right now, which are addressed by these PCIe addresses, they are inside the kernel network space or the kernel driver network space. We want to move one of them into the DPDK space, so let's do that. But you can see there are no other network devices. So first we need a network access to your FPGA board, which is the SDE instance. To be able to do that, we need to load an FPGA image that has SDE. And I'm showing you this image here, which is provided by Amazon. It's a public image. It has a sample SDE block that you can use for testing, or you can also use this for developing your own custom logic. So you can load this image onto the FPGA board using the FPGA global ID, image global ID. And you can see currently my FPGA slot is empty. There is no image running on it. So I'm going to load this image onto my FPGA board in slot 0. So I can load it with a single command in slot 0. And you can see it takes a few seconds to get loaded. And after I have loaded, you can see the status change from cleared to loaded. So now let us take a look at the SPP status again. So you can see we still have the two interfaces in kernel space, but now we have another interface which represents the FPGA block via the SDE access. So let us move the Ethernet 1 and this SDE into the DPDK space. So there are some sample scripts. These are available on AWS FPGA GitHub page. You can use the script to move this into the DPDK application space. And you can see that I'm moving the Ethernet 1 interface, which is on this PCIe address, which is also indicated with ETH1, inside the DPDK application space. And if I check the SPP status now, I have two interfaces in the DPDK environment, which is Ethernet 1 and the SDE. So now I'm ready to have my packet directly patched from Ethernet 1 interface into my FPGA boards. So I'm going to run the test PMD application. This essentially will just loop back the packet from an outside interface, the packet generator interface, through the FPGA board and back into the packet generator. If you can see in the forward mode, I have put the address swap. So I'm swapping the MAC address of the Ethernet 1 interface with the SDE. So SDE listens on to these Ethernet 1 MAC address and can respond and loop back from the FPGA shell. So we are ready with setting up the virtual Ethernet application. This application is now listening for looping the packets back, and now we can go into the packet generator instance. So we are in the packet generator instance. This is the M5 8X large instance that I showed on the left-hand side in the architecture. Let us check the interface configuration for this instance. Again, it has two interfaces. The ETH0 is for SSH and ETH1 for DPDK application. After this, let us check the current status of the software patch panel. So if you see, both the interfaces as expected are in the kernel space. There is no FPGA here, it's just a packet generator. So we will only need to move the Ethernet 1 interface into the DPDK application or the DPDK environment space. So I'm moving that. So you can see there is a script which is available. You can modify it as I mentioned. And I'm moving the Ethernet interface, which is on this PCIe address, into the DPDK environment. And if I check the status again, you can see the Ethernet 1 interface is now on the DPDK compatible driver space. So we have moved it from the kernel space into the DPDK application space. After this, I want to set up my packet generator configuration. So I have a small configuration file that describes what is the destination, what is the source, and what is the MAC. So you can see this source IP is the Ethernet 1 source IP of packet generator, and the destination IP is the Ethernet 1 destination or IP address of Ethernet 1 in the virtual Ethernet application. And that's the MAC address of the ETH1 interface. So with this configuration, I'm going to start the packet generation part. You can see the last part where I'm using the configuration file that I just described to fire up the packet generation piece. And the packets are now getting sent. You can see that I am sending jumbo frames as a part of the first flow. And I'm getting up to 8 Gbps. The networking bandwidth is up to 10 Gbps for 2x large instances, but I'm already getting 8 Gbps here. And this is really dependent on packet size. So I changed the size from jumbo frame to 64 bytes, and you can see the throughput reduced to 370 megabytes, right? And if I change and gradually increase the MTU or the packet size, for 512, I'm already reaching up to 2 gigabit per second. And you can see that my packets are increasing in that space. And if I go back to a jumbo frame now, like at 9,000, you can see I'm going back up to 8 Gbps packet flow. So essentially, your throughput is dependent upon the packet size, and you can really maximize the amount of throughput you can get from your FPGA board if you increase the packet size. And this just shows the snippet, like we are looping the packet back from the virtual Ethernet application back to the packet generator. So you can see the number of receive bytes and transmit bytes are same on the virtual Ethernet application. So that brings me to the end of this session and the demo. Thank you very much for attending the session. Please do not forget to provide feedback on the mobile app. We are really looking forward to hear feedback and see what we can change and what we want to hear about. And if you have questions, you can raise them now. We will also be at the PL Talk Lounge on 3rd floor here in MGM, so you can also see us there. But we are now open for questions.
Just one point before we jump into the questions. The code examples that Ajit showed today are available on the AWS GitHub repo. So you'll be able to go in and play with the Python scripts, look at the DPDK stuff. All of this is available to you on our GitHub. Just Google AWS FPGA GitHub, and it will come up for you. And then you'll be able to actually repeat this and do this yourself. Happy to take questions if anybody has questions.